So today our presenter is Dr. John Coxon from Northumbria University. John completed his PhD in 2015 at the University of Leicester. He then did a postdoc at the University of Southampton before becoming an STFC Ernest Rutherford Fellow at Northumbria University in 2022, where he's working now. And in 2025, John won an RAS Fowler Award. John's primary scientific expertise are in the Birkeland currents, which play a key role in space weather effects on Earth. So I'll now hand over to John's talk, which we can see is titled Hemispheric Asymmetries in the Solar-Terrestrial System. Thanks.
Hello, and thank you very much, Gemma. So today I'm going to talk to you about hemispheric asymmetries and whatnot. And I'll start by introducing the Birkeland currents, and then I'll move on to introducing the idea of asymmetries in our system, and I'll wrap up by explaining what I think the next steps are in that work. The work I'm presenting here has been done in collaboration with a large number of people, too many to list on the slide, but I'd just like to say thank you to everyone who's worked with me over my career, because without them I would not have been able to do any of this. So start off with Christian Birkeland. This is a photograph of Christian Birkeland taken in the early 1900s in his laboratory in what is now Oslo in Norway. Birkeland on the left, he's the one wearing the rather natty fez, and the big contraption in the middle is his Torella. And this was basically a machine he built which has a magnetised sphere in the middle of the vacuum chamber that you can see in the centre, and then he set up an electron gun and he would fire electrons at the sphere and see what happened. And the reason he was doing this is because he postulated in the 1890s that the aurora were caused by some stream of particles leaving the sun and interacting with the Earth's magnetic field and therefore being channeled towards the poles. And as we now know, the solar wind is a real effect, and it was discovered later on with spacecraft data. But this is his experiment he built to confirm that this was a reasonable theory using laboratory experiments. And this created an awful din, and it's written that because this lab was under a lecture theatre, it was very obvious when he was doing experiments because of the noise, and students would quite regularly leave the lectures to go down and see what he was doing instead, which made him unpopular with his teaching colleagues. He also invented the magnetic rail gun, but I won't go into that now. For his work on the Torella and for his subsequent postulation of field-line currents, he's commemorated on the old Norwegian 200 kroner note, and you can see there's a little line drawing of his Torella on the left-hand side of the note. But yes, this is our first kind of view of the fact that the solar wind might exist and that currents might flow along the magnetic field lines in the Earth system as a result of solar wind interactions. This was first discovered in data about 60 years later, and sadly after Birkeland's death. This was first discovered by Zmuda et al. In 1966. They observed magnetic perturbations, and then Cummings and Dessler in 1967 were the ones that actually proposed that the observations in 66 were the field-line currents that had been postulated kind of 60 years earlier. And there were various papers by Armstrong and Zmuda in particular, but a few others, which started to unpick the nature of these currents. And so you'll hear these called field-lined currents because they flow along the magnetic field lines at Earth, but you'll also hear them called Birkeland currents after Christian Birkeland. And it tends to be that people refer to them as Birkeland currents if they're the large-scale field-lined currents, whereas if you're looking at kind of small-scale microphysics, you call them field-lined currents instead. Although that's not a hard and fast rule, as with all nomenclature. And then in 1978, Tajima and Patemra published a paper which built on a couple of papers they'd published earlier in the 70s, which looked at the overall morphology. And this was a plot that they drew from hundreds of passes of a satellite called Triad. On the left-hand side, you have weakly disturbed conditions, and on the right-hand side, you have strongly disturbed conditions. And what you can hopefully see is that there are these kind of circles of current on either side of the noon-midnight meridian, which is the line kind of going in the vertical direction in the middle of these plots. The circles change polarity. So you've got currents flowing into the ionosphere on the right-hand side at the high latitudes, currents flowing away from the ionosphere at the high latitudes on the left-hand side, and then equatorward of those two, you've got currents of the opposite polarity. So you've kind of got these 4 current sheets almost. The currents that are closer to the pole we refer to as region 1 currents, and the currents that are towards the equator we refer to as region 2 currents. And as I say, they have different polarities on either side of the noon midnight meridian. And so this was kind of the state of the art in the late 70s in the currents, and I'm going to explain the Dungy cycle now because I need to explain the overall ionospheric convection that leads to these currents occurring. And so this is a video made by Patricia Reef after Dungy 1961, and I believe based on figures by Steve Milan, who is in the audience today. But effectively, the red line here is a closed field line, and the blue line on the left is a solar wind field line. And when I start the video, they're going to merge and interconnect, and you're going to get them move around the Earth. So here they merge, and then you get this natty purple line which moves round to the night side, and then you get reconnection again in the night side, and you have this large scale flow happening again. And this is called the Dungy cycle, and this governs a lot of the magnetospheric dynamics that we see at Earth. And effectively you get field lines being dragged across the polar cap above and below the Earth, and then they convect back round the dawn and dusk flanks to the day side again as part of this circle. So you've got this kind of Tai Chi effect around the magnetosphere. What does this look like if you're looking down at the polar cap? So imagine you're a spacecraft and you're above the North Pole and you're looking down at the Earth. So in this video, the blue dots are open magnetic field lines and the green dots are closed magnetic field lines. And if I start this video, we'll get day-side reconnection happening in a minute now. When day-side reconnection starts happening, you start getting these closed field lines converted to open field lines, and they move from outside this red line, which is the polar cap boundary, and they move inside the polar cap. When night-side reconnection starts, which is just happening now, you start getting open field lines being converted to closed field lines, and so you get this convection, this kind of dual cell convection, and these giant D shapes. The relative strength of the two reconnection rates governs whether the red circle expands or contracts. So right now the red circle is about to contract because the night side reconnection rate is above the day side reconnection rate. If the day side reconnection rate is stronger, then the polar cap expands. And what this does is it drives this large scale kind of twin cell convection in the ionosphere. And this is known as the polar cap, the expanding contracting polar cap paradigm, and it was first proposed by Cisco and Huang in 1985 and codified by Cowley and Lockwood in 1992. But the key thing is you get this anti-sunward flow across the polar cap, and then you get sunward flows returning around the flanks of the polar cap. And if you look at what this means for the electrodynamics, in this picture the solid lines, hopefully you can see my mouse, but the solid lines here are the large scale plasma flows, and because we know that the Earth has a magnetic field, the combination of those large scale plasma flows with the magnetic field of the Earth leads to electric fields which must form as a result of that interaction. And the electric fields point towards this vortex of plasma here and point away from this vortex of plasma here. And what that means is that you've got a build-up of charge here and the opposite situation here, and that means that you must have currents which are flowing out of the ionosphere here towards you, the viewer, and then you've got currents flowing into the ionosphere here away from you, the viewer, where your screen is the ionosphere, through the magic of technology. And you have currents of the opposite polarity which flow towards the equator to satisfy the electric fields that are flowing from these large-scale vortexes to the equatorward side. So you've got an electric field pointing poleward here, an electric field pointing equatorward here, so you get currents flowing in here and currents flowing out here. And these are the region 1 currents on the inside of this circle, and then these are the region 2 currents on the outer circle. And it turns out that the region 1 currents flow on this open closed field line boundary, which is the red line from the previous slide. So the overall convection set up by the Dungy cycle is a key part of how these currents flow and where they flow. This is a picture from a dataset called Ampere, which I will explain more a little bit later in the talk. But this is a snapshot of data rather than being based on hundreds of satellite passes built up over months. This is based on a spacecraft constellation that has 66 satellites, and you can take snapshots in 10-minute windows. And this is at about 11 p.m. on my birthday in 2011, and you can hopefully see that you've got downward current in blue here, an upward current in red here, and then you've got the opposite. You've got downward current on the poleward side here, an upward current on the equatorward side here, and that compares to the currents as presented in this theoretical schematic. And so hopefully you can see that these match up. What we have in the theory matches what we find in the data. And so I've described the region 1 and region 2 currents, which are these Birkeland currents, but they're part of a larger current system. So you get currents flowing along the magnetopores, they close through region 1, and then region 1 currents flow into the ionosphere, you get some ionospheric current flowing, it closes into region 2, which flows out to the ring current. The ring current flows around the equatorial plane of the Earth, and then you get current flowing back into the ionosphere, current flowing back out to the magnetopores, and you complete this large current circuit. So these currents fit into this much larger electrodynamic puzzle. And I'm not going to touch too much on this in this talk, but if you have any questions afterwards, please do let me know. So that's explaining the basics of the ionospheric convection and the electrodynamics that occur as a result. Now let's think about asymmetries. So we have asymmetries in geophysics, and I'm going to walk you through some of those, and then I'll get on to the research I've been doing. So it's been known that there are asymmetries in Earth's magnetic field for centuries, and there's a great paper by Zmuda et al. In 1971 where he goes through the history of some of these. Van Bemmelen in 1896 writes that he has drawn maps of the magnetic declination for the period 1540 to 1680, and this map here is by Ehrman in 1841 and shows Earth's magnetic field, and you can see that the magnetic field as drawn is clearly not symmetrical between the two hemispheres. So this has been known for a very long time. Coxon et al. In 2012 used the coupled magnetosphere-ionosphere-thermosphere model, and they predicted that Birkeland current strength should decrease with stronger magnetic dipole moment. And what that means is that if you know that your internal field is asymmetrical, you should probably therefore predict that the field-lined current or the Birkeland current resulting from that magnetic field might also be asymmetrical. And this is, to my knowledge, the first time anyone had proposed that this might be true. Looking at geographical asymmetries, we have coupling between our system, the solar-terrestrial system, and oceans and the neutral atmosphere. And we know that oceans are not symmetrical between the hemispheres. This is a neat graph that Andrew Kavanagh showed me at NAM, which basically lets you see the oceans as if they're one giant swimming pool. But you can see that Antarctica is in the middle here, and you can see that the amount of sea in the southern hemisphere is quite a lot larger than the amount of sea in the northern hemisphere, which is something most people know but perhaps haven't thought about carefully. And we also know that the atmosphere is not symmetrical between hemispheres. I had a look through the literature, and as far as I can tell, the first observations of asymmetrical CO2 behaviour, for instance, in the atmosphere go back to about the 1980s. So it's been known for decades that the atmosphere is not symmetrical between hemispheres. And obviously this includes the thermosphere, which is coincident with the ionosphere, which is the kind of part that we care about most due to the charged particles. Looking at the thermosphere, thermospheric winds have been found to be more variable in the southern hemisphere by Forster et al. In 2008, and a couple of papers by Forster and Ingrid Knosson in 2013 and 2015 established that neutral wind and ion drift velocities are both higher in the northern hemisphere. So this shows the neutral wind over the polar cap regions in the dipolar magnetic field assumption and the IGRF assumption. So the IGRF is the International Geomagnetic Reference Field, and it's based on data rather than just assuming a simple dipole. And what you can see is that the green line in this bottom plot shows that there is a substantial difference towards the north if you take the actual Earth's magnetic field rather than assuming a simple dipole. And if I show you the ion drifts, you see a similar situation. the north has higher velocities of ion drift if you use a realistic magnetic field. And if you're interested in finding out more about hemispheric asymmetries, I would highly recommend you go and read Kalle Laundal's paper in Space Science Reviews from 2017. Myself and various others on this call are co-authors on that paper, and it's very good. And there was also an excellent seminar by Ingrid Coxon in November 2022, and I've put the title slide here, so I would highly recommend going and watching that if you have a spare hour in your afternoon. Okay. So let's focus on the asymmetries in the electrodynamics themselves now. So we are going to start here with auroral asymmetries. So there was a Nature paper by Laundal and Osgaard in 2009 where they presented this graph I'm showing on the right. And effectively there were two auroral images called image and polar, and they coincided in orbit for a brief period, and therefore there is a small data set of conjugate observations where one of these spacecraft observed one hemisphere and the other observed the other. These are not truly conjugate because the wavelengths are different between the cameras on these spacecraft, which I'm going to get back to later, but they showed for the first time that basically if you looked at the aurora in both hemispheres, they were not conjugate. There were differences. There were asymmetries. I have mostly been using a dataset called Ampere, which I promised I would show you. And this is a constellation of telecommunication satellites known as Iridium. And those satellites orbit in 6 orbital planes, and there are 66 satellites, so that's 11 per plane. And basically the amount of time it takes for a satellite to reach where the previous satellite was is 10 minutes. So you can take the magnetic data from these satellites and you can evaluate the currents that would need to occur for the magnetic perturbations you measure with those satellites, and you can do that in a 10-minute long window. And that window is evaluated every 2 minutes. So you kind of get data between a 2 or 10 minute cadence depending on who you're talking to at your conference poster. These data are available from 2009 to 2025, and they're presented on a grid of 1 hour MLT by 1 degree latitude. So this is a phenomenal data set to look at various things, but the obvious point to this seminar is that there are satellites up here at the north and down here at the south. So it's good for looking at hemispheric asymmetries as well. So what we can do is Ampere gives us these maps of field line current, and I've already shown you one in this talk. This is just from a paper I wrote in 2022. These are maps of the mean and mode current from Ampere, and these are just to illustrate the sorts of morphology you might get on average. But effectively you get these maps. You get maps from Ampere on a cadence of 2 to 10 minutes. And what you can do is you can integrate over these maps and you can find the total amount of upward current and the total amount of downward current, and you can sum them to just get the total amount of current that's flowing. And then you can plot the difference between the current flowing in the north and the current flowing in the south, and you can determine which one is stronger and what affects that. And in 2016, I published a paper. We were originally just looking to capture the seasonal variations in the currents due to changes in ionospheric conductivity, but we ended up finding something else. So this is a plot from that paper. This is the north minus the south. So the dashed line at 0 indicates parity between the two hemispheres, and if the line is above 0, then you've got an asymmetry bias towards the north. And if you've got the line below 0, then you've got an asymmetry towards the south. And the lovely fetching ice cream parlour pink and light blue stripes show the summers and winters. And so what you can hopefully see is that the north dominates. So you've got this situation where the north has more current than the south at almost all times except for the southern summers. So when the southern hemisphere is in the most sunlight, then there's more current in the south, but at all other times the north is stronger. And this indicates that there is some sort of systemic asymmetry towards the northern hemisphere in the amount of current flowing. We investigated this a bit further in the paper, and we basically compared it to modelled results from a simple model of the Birkeland currents driven by reconnection that was written by Steve Milan in 2013. And we took the original model and then we modified the model by including more realistic treatments of the ionospheric conductivity due to photoionization, due to insolation. And we found that although the correlations are quite high, you can see here we get correlations of kind of 0.87, 0.86. The blue cloud, which is the southern hemisphere points, is kind of offset from the red cloud, which is the northern hemisphere points. And the model predicts the southern hemisphere points pretty well, but the northern hemisphere points it is systematically underestimating. And this again shows that the northern hemisphere currents seem to be systematically stronger than the southern hemisphere currents, even when you account for the seasonal effects using this model. And I'm going to start using something called the asymmetry index. So instead of just doing north minus south, I'm going to start talking about the percentage difference between the two hemispheres. This is something that was used by, I think it was introduced by Hong et al. In 2021 to talk about asymmetries in a different context, but it was also used by Wang et al. In 2023. And basically it's the difference divided by the mean, which basically gives you this percentage difference between the northern hemisphere, or N, and the southern hemisphere, or S. And so if I say A is above 0, what that means is that the northern hemisphere is dominating. So here we see that this has been found in other satellite missions as well in the Birkeland currents. So I showed this with Ampere, but there was an open question as to whether or not this was a data artifact in Ampere or whether it was a real effect. Fortunately, people have since seen it in swarm and DMSP data, and you end up finding that, I ended up finding in my Ampere paper that the asymmetry was about 27% plus or minus 10%. Workiyehu using swarm data found a slightly more modest asymmetry of 12 plus or minus 4%, but in both cases that's statistically significantly above 0, so hurrah. This is a picture from the Workiyehu paper, and he argued that this asymmetry became less pronounced at higher geomagnetic activity, and he did that by binning in KP index either side of 2. This has also been seen in pointing flux. So the right hand side is a plot from a Nature Comms paper by Ivan Pakotin et al. And you can see that the northern hemisphere and the southern hemisphere, the north is above the south here. But this has also been seen by other authors. So Dolores Knipp et al. In 2021 showed that the asymmetry in pointing flux was about 25% towards the northern hemisphere. Dan Billett quantified it in swarm and found that it was between 9 and 28%. And an empirical model based on fast data showed that it was about 30% in 2022. So this is showing a different quantity, but a related quantity to the field line current. I'm going to use this model which we used in 2016, and I've christened it the FACER model, which stands for Field Aligned Currents Estimated from Reconnection, which I'm very proud of. I've also got a new model which I've managed to call Face Off in tribute to Nicolas Cage, the finest actor of our era. But I'm quite happy with this. But basically this is an extension of the 2016 model. It treats the conductivity slightly more realistically, and it has a couple more user configurable options that you can use. But effectively this is parameterized by UT and hemisphere. It's parameterized by the day side and night side reconnection rates. It's parameterized by F10.7, which we basically use to capture how active the sun is being. And it's parameterized by the radius of the R1 and R2 current ovals. And the real important thing I want you to take away from this is this model captures the asymmetry in the current due to seasons. So the modelled results capture the seasonal asymmetry. And you can use this. If you'd like to use it, you can do pip install FACER model, and you can play around with it. If you do use it, please cite the original Milan paper and please cite the Coxon paper. But yeah, go and have fun and draw graphs. It draws graphs for you. It's great. So yeah. So this is a plot showing Ampere data from late 2009 up to 2025 in blue. And this is the asymmetry between the two hemispheres as evaluated from the total current measured by Ampere. And then the orange line is the asymmetry in the total current predicted by the phasor model. And we basically run the phasor model at all integer UTs for each day and then take an average. The details are in the paper. What you can hopefully see is that you've got this sinusoidal behaviour in the model and in the data, where in the northern summers the asymmetry is towards the north, and in the southern summers the asymmetry is towards the south. That's good, that's what we would expect from the seasonal behaviour. Because we capture that seasonal behaviour in the model, what we can do is we can subtract the asymmetry in the model from the asymmetry in the data to capture the residual asymmetry which we find that isn't explained by the seasonal variation. And so what I'm going to show you on the next slide is the residuals once you've subtracted that seasonal behaviour. Something I do need to note here is the eagle-eyed might notice there's a honking great big data gap in about 2018, and they might also notice that the data behaves somewhat differently after that data gap. And if you have noticed that, well done, gold star. But basically, this is because 2010 to 2017, the Iridium telecommunications network was using what they call Iridium Block 1 satellites, which are this older satellite bus. And in 2018, well, late 2017 really, they started replacing this constellation with newer vehicles, which they called Iridium Next. And I won't go into details on that, although I can do if you want to ask questions later. But effectively what this means is that the Iridium Next spacecraft have better attitude control, and so your ability to resolve the direction of the spacecraft is better, and so you can resolve finer scale magnetic perturbations, which means that your data from the satellites gets more variable after the data gap. So that's the first key difference. The second key difference is that the Ampere team began to start using a new processing pipeline for this data, and they made this switch sort of late last year, early this year. And instead of using the world magnetic model to baseline the data, they're using Chaos 8.1, which is a different model. But they've also got this new processing step where they use something called spherical elementary currents to treat the current maps before they remove the magnetic model. And so there's a difference in the way the data are processed, and that's important. And it turns out that this is the residuals now, so this is removing that seasonal asymmetry behavior. And in the original data with the original processing method, your asymmetry is about 21%. In the new spacecraft with the original processing method, your asymmetry is about 19%. So that's a small change, but it's not statistically significant. And it means that the change in satellite bus didn't affect the measurement of the asymmetry significantly. However, when you use the new processing method, your asymmetry goes to 4 plus or minus 2%, which is still significantly above no asymmetry, but is quite a lot smaller than the reports from the older processing method. And it's notable that you go from being about twice the asymmetry estimated using other spacecraft missions to about half the asymmetry estimated from using other spacecraft missions, which makes it very difficult to tell which one of those three methods is the one that's giving you the true asymmetry. So the asymmetry has seemingly gone from being over-predicted to being under-predicted, and it's difficult because we don't have a ground truth to assess which one of these is the most valid way of doing this. So this brings me to my soapbox. This is a soapbox which has been stood on by many luminaries of the field, including Steve Milan, Johnny Ray, Mike Limone, and others. And the soapbox is this: we need dual hemisphere auroral imaging from space, please. So this is the only way to take truly conjugate measurements of both hemispheres, and we don't really currently have that capacity. Ampere is the closest we have, but even Ampere, the satellite tracks in the southern hemisphere are different enough from the satellite tracks in the northern hemisphere that it's unclear what the best way of processing the data to make them equivalent is, and you can get different processing methods which lead you to wildly different results. So in order to address this, we need to just put some cameras up there and take some photos. So this is something I've submitted to the UK Space Frontiers exercise in a white paper, and it's something I'm thinking about more and more. This is a picture from that Laundel and Oscard paper in 2009 where they used polar and image data. The problem with polar and image data is firstly there's not many conjunctions, and secondly Wick on image and Viz on polar measured in slightly different wavelengths. So image is telling you really about the behaviour of nitrogen molecules and atomic nitrogen, whereas Viz is mostly telling you about atomic oxygen. And so it's good, it's a start, it's not truly conjugate. It gives you an idea, but it doesn't give you the whole picture. And there's also X-ray aurora at Earth, and this is images from Pixie, which is from a paper by Petronek et al. In 2000. But there's never been conjugate measurements of X-ray aurora in both hemispheres. We've never had that capability. There's also another thing to do with the aurora, which is auroral kilometric radiation, or AKR. This is radio emission in the 50 to 800 kilohertz band caused by wave-particle interactions with electron beams. And these are associated with energetic processes, so substorms is an obvious example. And there's a couple of papers by Waters, James Waters, which I'm on, which look at how AKR is associated with substorms. And if you're interested in more details, then I highly recommend going and read those papers. I think they're really interesting. But again, we've never had dual measurements of this from both hemispheres. So we have some science questions, which is firstly, how is our system asymmetrical between the two hemispheres? And we're beginning to make progress on that science question without this mission, but as I hopefully persuaded you with the vastly different results from the different Ampere processing methods, this is actually quite a hard question to answer without having a spacecraft mission designed to answer it. And so let's answer how it's asymmetrical, let's get that out of the way. And then let's answer why. What causes the asymmetry? Like, once we've worked out what the asymmetry is, let's work out why it happens. So is that solar wind conditions? Is that because Earth's internal magnetic field is asymmetrical? Is that because the ionospheric conductivity is asymmetrical? Is that due to coupling with other factors, geographical or otherwise, that are asymmetrical? We don't know. Let's figure that out. And then thirdly, what causes asymmetries on mesoscales and below? So once we've identified and explained large-scale asymmetries, can we start looking at the smaller scales and how those are asymmetrical? So science question 1 for this hypothetical mission would be to characterise this asymmetry. And like I've said, there are real issues with data sparsity. And with a ground-based approach, you're struggling because Antarctica is smaller than the Arctic Circle. You've basically got a small island surrounded. Describing Antarctica as a small island when it's a continent might be controversial, but you've got a landmass surrounded by ocean versus an ocean surrounded by landmass, so the ground-based approach is difficult. And space-based approaches either rely on low numbers of satellites built up into empirical models, or they rely on global approaches like Ampere, but then you still have issues with orbital tracks. Science question 2 is understanding this asymmetry. So is this caused by asymmetries in the eternal dipole? So these are plots from Workiyehu et al. And Laundel et al. That basically show the magnetic poles overlaid on the geographic map to show you how the magnetic poles are asymmetrical between the two hemispheres. And you've also got the neutral wind asymmetries, which I mentioned earlier in the talk. Is it possible that those are what's driving this? We don't know. Let's find out. And then science question 3, mesoscale asymmetry. So we know that auroral beads are a precursor to substorm onset. It's been found in equatorial ionospheric physics that you can end up with phenomena driven by wave instabilities in one hemisphere, but the wave instability is happening in the other hemisphere. And so they've actually got observations where they're seeing a phenomenon in a hemisphere which is being driven by the other. And so does that happen at high latitudes? That is not well understood. And that's one of the questions I think we can make progress on. So proposed instrumentation, I would like ultraviolet imager and an X-ray imager and a radio wave imager, please, and thank you. If anyone's on the call who's got a spare few £1,000,000, do let me know. We don't need in situ instrumentation. It's unnecessary for what we want to do. There's enough in situ measurements out in the magnetosphere already, and it would just encourage scope creep in our mission. So I think that is probably something to avoid. We need to be able to see various physical phenomena. So what we would quite like to know is we'd quite like a UV imager that could see Lyman alpha, to see proton collisions, and then we'd quite like UV measurements and X-ray measurements to show us electron collisions with oxygen and with nitrogen, or energetic electron collisions, and also wave particle interactions with beams would be something we could see with AKR measurements. There are some existing instrument concepts which could deliver this. There's a paper out of Leicester in 2007 by Nigel Bannister et al., the wide field auroral imager, which looks great, and I think that would be very good. There's another concept by Calcines Rosario at Durham, and this is designed to look at the UV spectrum of the sun, but I think you could use a version of that instrument in an Earth-based mission, and I've talked to Adriana about that a little bit. There's a concept for an auroral X-ray imaging spectrometer by Cruz et al. In 2024, and there was a instrument aboard the Jupiter Icy Moons Explorer, which would suit our mission nicely. So this isn't something we'd have to do a bunch of new instrumentation to do. The concepts for this are already out there, really. As this is just a nice table for the YouTube, which shows exactly what we would like. To do the mesoscale stuff, we would need instrument requirements 5 and 6, which is looking at small spatial resolutions and trying to do that at high cadences. So that's why those are there. So I'll conclude and leave sort of 10 minutes or so for questions. But we've known that Earth is hemispherically asymmetrical for centuries in the case of the internal field. We've known it for decades in the case of the ocean and atmospheric physics, and we've known it for about 20 years in solar-terrestrial physics. But that knowledge is beginning to kind of become more and more. There's more and more people working on this topic, and it's becoming more and more of a thing that people are paying attention to. So that's very good. However, it's very difficult to analyse because of all of these issues with data sparsity that I've described, and so I would quite like to have a dual hemisphere auroral imager to look at this phenomenon. Thank you very much.